Let us now talk about binary search tree. In binary search tree, data is organized in a way so that when you are searching an item, you can skip almost half of the items. The idea is based on binary search algorithm on arrays. In binary search, we go to the middle. If we find the element at the middle, we say this is the element we are searching. And if the middle element is greater, then we go to the left half. If the middle element is smaller, then we go to the right half. On this idea, we have a data structure which is not an array, which is a linked data structure, which is basically a binary tree, but it provides faster search. Let us take a look at this example binary search tree. The root of this binary search tree is 50, and all the values on left of it are smaller than 50. And all the values on right of it are greater. 30, all the values on left of it, 30, have to be smaller, and all the values on right of it have to be greater. For 70, all the values on left of it have to be smaller than 70. Also, these values have to be between 50 and 70 because they have to be greater than 50 and smaller than 70. This value has to be greater than 70. When we talk about binary search trees, we generally consider distinct values only. So in most of our algorithms, we are going to consider distinct input only. Third point about binary search trees, it is like linked lists in a way that it is a linked data structure. It's not like an array where everything is stored at one location. So it has certain advantages and disadvantages. In linked data structure, you never require resizing. Whatever elements you all want to insert, you can always insert the new items as long as you have memory available. You have this disadvantage of not being cache friendly. Since the items are at different locations, your data structure, like binary search tree, is not cache friendly. Since your items are at different locations, so data structures like linked list, binary tree, binary search tree, these are all not cache friendly. If we talk about binary search tree implementation in libraries, in C++, binary search tree is implemented by the map container, set container, multi-map, and multi-set containers. All these containers, they implement binary search tree. In particular, self-balancing binary search tree. In Java, there are containers, tree set and tree map. They also implement self-balancing binary search tree. We'll talk about self-balancing binary search tree in the upcoming videos. Let us now talk about example operations on BST. Before we move on to these operations, let me just clarify this thing. Binary search trees are represented same as binary trees. So if you're talking about C++ programming language, you are going to have int key, then you are going to have left and right pointers. If you're talking about Java programming language, then you are going to have int key and left and right references. So it's similar to binary tree internally. The only thing is, binary search trees have a specific insert operation. There is an order when you are inserting elements in a binary search tree. It's not like this, anything can go anywhere. There's no order in the binary tree. Also, the order has to be maintained when you are deleting an item. Let us discuss these operations. So when you say create an empty BST, it is like creating an empty binary tree which has a root pointer or reference whose value is null. And then you insert this key 20. So 20 becomes the root. Now you want to insert 15. You compare 15 with 20. 15 is smaller, so it goes to the left side. When you insert an item, you begin with the root. You keep comparing, you come down, and you insert whenever you find an empty place for insertion. So 20 is left is empty. So you will insert 15 here. 30. It's greater than 20. Let us now insert 30. We'll begin with the root. It's greater than 30. It's greater than 20. So we'll go to the right side. And we find an empty place on the right side, so we insert it. 40. We'll begin with the root. 40 is greater, so we'll come here. 40 is greater than 30, so we need to insert the right side, and there is an empty place, so we'll insert here. 50. we will begin with the root. It's greater, we'll come here. It's greater, we will come here. It's greater. And we have an empty place, so we'll insert 50 here. 12, it's smaller than root, so we'll come here. It's smaller than 15, so we'll come here, and we have an empty place, so we'll insert it here. 18, smaller than root, we'll come here. Greater than 15, we'll go to the right side, and we have an empty place, so we'll insert 18 here. 35, we begin from here. It's greater, so we'll come here. It's greater again, so we'll come here. And here it's smaller, so we'll come here, and we have an empty place, so we'll insert 35. 80. I think you must have guessed. It's greater, so we'll come here. We'll see again greater, so we'll come here. We'll see again greater, so we'll come here. It's again greater, so we'll come here, and we insert 80 here. 7. I think you must have guessed this now also. It's smaller, we'll come here. It's smaller, we'll come here. It's smaller, we'll come here. And we have an empty place. 7. So when you are inserting a smallest value, it goes to the leftmost child. And when you insert a greatest value, it goes to the rightmost thing. Here is one more example of insertion. When we insert these keys, we get this binary search tree. It looks like a linked list. All the things are connected in a chain. This happens when you insert items in increasing order or decreasing order. In this case, we are getting a chain like this. If you insert in decreasing order, you will get a chain like this. Everything will go to left, left, left. One interesting thing about binary search tree is most of the operations on binary search tree, whether it is search, insert, delete, or finding the closest, all of them are big O of h, where h is height of the BST. Also the variations of closest, like finding the floor, finding the ceiling, finding a greater value, smaller value, all these are also big O of h. So height of BST matters a lot. If you create a BST like this, all the operations on binary search tree are going to be big O of n, because n is the height of such a BST. But if you have a BST which is balanced, which has root and then 2 children, and these 2 children have 4 children, then every operation becomes big O of log n. So ideally, you would want to have a balanced binary search tree. In the next set of videos, we'll talk about search, insert, delete, floor and ceiling operations. We'll analyze their time complexities, which is going to be big O of h. And then we are going to talk about cell balancing binary search tree, where h remains big O of log n.